Okay, today we're going to start our study of electricity, magnetism, and electromagnetism. And this is actually going to take us 4 weeks, so this is our first week of this chapter. Let's start out by talking about electric energy. We know that electricity carries energy because that's what we use for most of our energy needs. And we know that we can just plug into the wall or we can put a battery in a device and we get energy out of it. One of the reasons that we use electric energy so much is that it's so convenient because it can easily be converted to different types of energy. And if you think about some devices that do this, an electric motor takes electric energy and converts it to kinetic energy. So we get something moving or spinning when we use a motor. Another example of a conversion of electric energy is a toaster. A toaster converts electric energy to thermal energy. If you've ever looked inside the toaster, you'll see these little thin wires that heat up when you put electricity into them, and when they heat up, of course, that's thermal energy. A combination of those actually is a hairdryer. If you think about what's inside a hairdryer, it's the same little wires that you find inside a toaster, plus an electric motor to blow air across those heating coils. So electric energy can easily be converted to other types of energy. Now the reason that that's relevant for us is that that's actually what an X-ray imaging system does. If you think about it, you take your X-ray imaging system and plug it into a wall outlet that's providing electric energy. But of course what we need is we need electromagnetic energy, meaning the energy of electromagnetic waves. And so when we plug in our X-ray system, we're taking electric energy and we're converting it to electromagnetic energy in the form of X-rays. And that conversion actually takes place in the X-ray tube, and that's something that you'll be learning about much more in your next course. Well, let's start talking about electrostatics. Static means not moving, and so electrostatics is the study of stationary electric charges. Now, you already know lots about electricity from previous courses, and one of the things that we all know is that there are two kinds of charge. One type is called positive and the other is called negative. And we actually have Ben Franklin to thank for that naming of positive and negative charges. So we have two types of charge, and we know that like charges will repel each other. So these two charges, since they're the same, are pushing each other away. And unlike charges will attract each other. So if I take a negative charge and a positive charge and hang them near each other, like in this picture, they're going to be attracted. And I'll show you a demonstration of that in class. Now, the reason that we have charge, positive and negative, is it really has to do with the fact that charge is a fundamental property of matter. We've talked about the fact that all matter is made up of atoms, and atoms consist of protons, neutrons, and electrons. Well, protons are positively charged, and electrons are negatively charged. Neutrons have no charge, so they don't contribute to electricity at all, but protons and electrons have positive and negative charge respectively. Now, one of the interesting things about this is, remember, an atom normally has the same number of protons and electrons. And of course that's true as long as the atom hasn't been ionized. So in that case, the overall charge on the atom is zero. It's neutral because it has an equal number of positive and negative charges. But once an atom has been ionized, then it has a net charge to it. One of the important things to understand about electric charge is that charge is conserved. And when we say something is conserved in physics, what we mean is that the total amount of it doesn't change. So what we mean by this in terms of charge is not created or destroyed, but it's simply transferred from one object to another. And you'll notice that that's the same idea as conservation of energy, that energy isn't created or destroyed, but it's transferred from one object to another or from one type to another, as we've talked about previously. Just to give you an example of the fact that charge is conserved, you're probably all used to the fact that in the wintertime especially, if you kind of scuff your feet along the carpet, when you touch a doorknob you might get a shock. And what's going on here is simply that electrons are being transferred. Let me try spelling that again. Electrons are transferred to your shoe. So in other words, it's not that charge was created or destroyed, it was just transferred from the carpet to your shoe, and then when you touch the doorknob it gets transferred again, and that's when you feel a spark. An object, we say, is electrified when it has a different number of electrons than protons. And again, we talked about this a minute ago, that in a standard atom, the number of protons in the nucleus, in this case that diagram is showing 2, is equal to the number of electrons that are orbiting the nucleus. But if we lose or gain electrons, then the object becomes electrified, meaning it has a charge. Well, one of the ways that an object can become electrified is charging by friction. And we just used that example when we talked about scuffing your feet on the carpet. And I'll show you some other examples of that in class. Another way that an object can become electrified is by contact. So when one charged object touches another object, it can pass charge to it. And that's actually what's happening when you touch the doorknob and get a shock. You're passing charge from your body to the doorknob. Another way that an object can become electrified is charging by induction. And in that case, charges move within the object. And it's much easier to show you that than explain it here. So I'll demonstrate that to you in class. One of the interesting things about the Earth is that because it's so big compared to us and everything else on it, the Earth basically acts as a huge reservoir for charges. And so oftentimes in a circuit, we connect to what we call the ground, simply meaning that we connect a wire down into the Earth. And in fact, where the electric power comes into your house from the power company, there's actually a big metal rod that goes down into the ground that helps protect you from getting electrocuted. So we use the Earth as a reservoir of charges, either to absorb charges or to provide charges. And that's in fact what the third prong in a plug connects to. So if you picture a typical plug, you've got your 2 slots, and then you've got that prong down there. That actually is connected directly to the Earth. The SI unit of charge is the Coulomb, and a Coulomb is actually a pretty big unit of charge. So if we look at what is the charge on an electron or on a proton, as we've said, electrons are negatively charged and protons are positively charged. And you can see that in coulombs, the charge on one electron is very small, negative 1.6 times 10 to the negative 19th coulombs. Or for a proton, 1.6 times 10 to the negative 19th coulombs. So remember, a negative power of 10 means a very small number. So here's a question. How many electrons are there in negative 1 coulombs of charge? Well, we just said that the charge on one electron is negative 1.6 times 10 to the negative 19th coulombs. So in other words, that's coulombs per electron. And what I want to do here to figure out how many electrons are there in 1 coulomb of charge is I would just take the total charge, which is negative 1 coulomb, and I would divide by the charge on one electron, which is negative 1.6 times 10 to the negative 19th coulombs per electron. And when I work that out, what you get is 6.25 times 10 to the 18th electrons. you'll notice that Coulombs cancels out, and you have 1 over electrons, which is just electrons. So the point of doing that calculation is just to show you that there are a whole lot of electrons in 1 Coulomb of charge. And that's why when we think about electricity, we often think of it as continuous, like a fluid, because just like we think of water as a fluid, even though it's made up of individual atoms, electrons or electricity acts like a fluid because there's so many electrons in any kind of charge that you're going to encounter. Let's talk about Coulomb's law. Coulomb's law is the law that describes the force between two charges. And so if we take two charges, like a positive charge and another positive charge, or it could be a positive charge and a negative charge, the force between those charges increases as I decrease the distance. Also, the bigger the magnitude of each charge, so if I have charge A and charge B, the amount of charge on each one, the more charge there is, the greater the force. Well, that's basically what Coulomb's law says. It says the force between two charges is equal to K, and K is just a constant, it's just a number that makes the units work out. So the force is equal to the charge on object 1 times the charge on object 2 divided by the distance between them squared. And you'll notice that this is another inverse square law. And remember, anytime we have something that is proportional to 1 over the distance squared, we call that an inverse square law. And so what we see from this is if we double the distance between two charges, so if we double the distance between two charges, then the force would be a fourth as much as it was. Okay, so that's Coulomb's law, and we're not going to solve problems with it, but just conceptually it's an important law to understand that if I increase the charge on either object, the force goes up. If I increase the distance between the two charges, the force goes down. Your book refers to 4 laws of electrostatics, and I just want to go over what those are. So we've really covered 2 of them already. The first one is just that like charges repel and opposites attract. The second is Coulomb's law, which again we just talked about, that the force between two charges is proportional to each of the charges and inversely proportional to the square of the distance between them. The next law that's covered in the book is that electric charges distribution is uniform throughout or on the surface. And let me talk a little bit about that. Imagine that this is a piece of metal. If you think about it, charges can move very easily in metal, and we'll talk more about that in a second. And so if I have some charge on a piece of metal, all the little charges are going to want to get as far away from each other as they can, because like charges are repelled. And so what that means is that those charges are going to end up on the surface of the object. Also, if charge is distributed on an object and the object has a sharp point, there will be more charge located at that sharp point. So electric charge in a conductor concentrates along the sharpest point of curvature of the surface.